Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video, I will be solving the paper 4 exam for October-November 2024, variant 1. So let's get started. Question 1 says a spring is suspended from a clamp. Figure 1.1 shows a pointer attached to the lower end of the spring. We have the setup here in the diagram. A student suspends loads of different weights from the spring and records the readings on the meter rule. Figure 1.2 is the reading weight graph that the student obtained. So we have length against weight. Part AI says using figure 1.2, determine the reading on the meter rule when no weight is attached to the spring and when a weight of 5.6 Newton is attached to the spring. So at force 0 newtons, we have a reading here. Each small division makes 2, so that's between 42 and 44, that's 43. So this is 43 centimeters. And another reading for the force of 5.6 newtons. So we go on the x-axis, 5.5, 5.6. Going up to the graph, we have this level here. Going to the y-axis, this is between 62 and 64, so this is 63 centimeters. We write down the answer. Double I says calculate the extension of the spring when the weight attached is 5.6 newtons. So the extension is equal to the extended length minus the original length. We have extended 63 and original 43. That gives an answer of 20 centimeters. Part B says using the values found in A, calculate the spring constant of the spring. The spring constant is equal to the force divided by the extension, and the force was 5.6 newtons, and we have the extension as 20. That gives an answer of 0.28, but the force was in newtons and the extension was in centimeters, so that's newtons per centimeter. Part C says an object of mass 0.50 kilogram is attached to the spring. Calculate the weight of the object. We can use W equals mg. The weight is equal to 0.50 multiplied by 9.8, which is a gravity field strength. That gives an answer of 4.9 newtons. Double I says the object is pulled downwards until the tension in the spring is 6.5 newtons. The object is released. Calculate the acceleration of the object immediately after it is released. So we have here a force in the spring equal to 6.5 newtons upwards, and the weight of the object itself is 4.9 newtons. Using the equation F equals ma, F is the resultant force, so we use 6.5 as the force with motion minus 4.9, which is a force against the motion, equal to the mass, which was given 0.50 multiplied by the unknown acceleration. Then we divide by 0.50 on the left side. That gives an answer of 3.2, and the unit for acceleration is meters per second squared. Question 2 says a drag car is a racing car that is powered by a rocket engine. A drag car accelerates uniformly from rest until it reaches the finishing line. The engine is then switched off and the parachute opens. The car decelerates until it stops. Figure 2.1 shows a drag car decelerating after a race. This drag car has a mass of 1,400 kilograms. Figure 2.2 is the speed time graph for the car during the race on a straight horizontal track. So we have constant acceleration at the first part, then decreasing deceleration shown by the decreasing gradient of the graph. And it says that the car reaches its maximum speed of 130 meters per second at time 6.5 seconds. Part AI says calculate the maximum momentum of the car during the race. So momentum is equal to mass multiplied by velocity. The mass of the car was given at the start of the question, 1,400 kilograms, and the maximum speed was given as 130 at the end of the last page. That gives an answer of 1.82 times 10 to the power of 5, and the unit for momentum is kilograms meters per second or Newton second. Double I says state the feature of figure 2.2 that represents the distance traveled by the car. It is equal to the area under the graph, and if we are required to calculate the acceleration, it is the gradient of the graph. Triple I says determine the distance traveled by the car in the first 6.5 seconds. So that would be the part under the straight line, which looks like a triangle. So we have the base is 6.5 and the height is 130. So we write down distance equal area, and then we substitute half times base 6.5 times height, which is 130 meters per second. That gives an answer of 422.5. So we can approximate that to 423 or 420, and the unit for distance here is in meters. since the speed was in meters per second. Part B says the parachute opens at 6.5 seconds and the car decelerates. Describe how figure 2.2 shows that after 6.5 seconds. So the curve was going this way, so decreasing value on the y-axis, or that the line has a negative gradient. So that's what I'm going to write here, negative gradient. Double I says the deceleration of the car is not constant. How does the graph show that? That's because the line is curved and not a straight line. So say that the graph is not a straight line. Part C says describe the energy transfer that takes place as the car slows down. So a moving object has kinetic energy, and as it slows down, the kinetic energy is converted into something else. So we start with kinetic energy and we say that is converted to, in this case, we have the air resistance from the parachute, and air resistance is a form of friction, and friction generates heat energy or thermal energy. Question 3a says define the moment of a force and describe the effect that it measures. So it is the product of the magnitude of a force and the perpendicular distance from a pivot, and it measures the turning effect of a force. Part B says a large rectangular block of stone has a square base of side 3.4 meters. Figure 3.1 shows the block at rest on a horizontal surface. The block is of uniform density, which means that the center of gravity is at the geometric center of the shape, and the center of gravity G is at its center. Explain what is meant by center of gravity. It is a point where the weight is assumed to act, or the point where the mass is assumed to be concentrated at. Double I says the weight of the block is 1.3 times 10 to the power of 7 newtons. Calculate the moment of the weight of the block about the corner x. So going back to the diagram, we have the force of the weight acting here, and the perpendicular distance between the weight and x is actually half the width of the rectangle. So we calculate half of the 3.4 meters to get this part, which is a perpendicular distance. So we multiply the weight, 1.3 times 10 to the power of 7, which is a force, and the perpendicular distance is 3.4 divided by 2. That gives an answer of 2.21 times 10 to the power of 7, or we can approximate it to 2.2 times 10 to the power of 7, and the unit here is Newton meter, force multiplied by distance. Part C says the block shown in figure 3.1 is in equilibrium. State the two different conditions that apply when an object is in equilibrium. So we have no resultant force and no resultant moment, or we can say that clockwise moments balance anti-clockwise moments about a pivot. So there is no acceleration for the resultant force and no rotation from the moment. Question 4a says describe an experiment to determine the specific heat capacity of aluminium. You may draw a diagram, include in your answer the measurements made and any equations needed. So we have a solid block of aluminium and we need to get the specific heat capacity, and the equation for specific heat capacity is Q equals mc delta theta. Q is the heat energy supplied, m is the mass of the material we are testing, C is the specific heat capacity, delta theta is the change in temperature of the object. But since energy cannot be directly measured using any apparatus, we can use an electric heater of known power and multiply that power by the time of heating. So power multiplied by time, that gives us energy. So this is Q. The mass, we can use a balance. Specific heat capacity is a required calculation, and change in temperature is actually not a measurement, it's a calculation. So we need to measure the initial and final temperatures to get the change in temperature. So I'm gonna draw, for example, a cylindrical block of aluminium like this, and we have a hole here for the heater. For example, I'm gonna draw a smudge here and two connecting wires, and I'm gonna label this heater connected to power supply, and this is the aluminium block, and I'm gonna place it over a balance, drawing it like this. You do not have to draw it as 3D as I draw it, just draw a rectangle and call it balance or top and balance. And I'm gonna make another hole for the thermometer and just a stem here and label it thermometer to measure the temperature. Now for the readings, we have time of heating, I'm gonna call it T, the mass of the block, I call it M, initial and final temperatures, I'm gonna call them theta 1 and theta 2, the power of the heater as a given, I'm gonna call it P, and then we use the equation C is equal to PT, which is the energy, divided by the mass and the change in temperature. And I'm going to say that the change in temperature is calculated as θ2 minus θ1. Part B says an aluminum dish is initially at room temperature. Boiling water is poured into the aluminum dish, as shown in figure 4.1. Part I says explain why after a short time the dish and water are at the same temperature. So this is due to transfer of heat energy. We say at first the hot water gives thermal energy to the dish until they are at the same temperature and there is no more net energy transfer between the two objects. This is called thermal equilibrium. When two objects are at the same temperature, there is no net energy transfer between them as heat. Part double I says explain in terms of its particles why the aluminum expands as the boiling water is poured into the dish. So we say that particles vibrate faster since they are in solid state, and the spaces between them, between the particles, increases, but the actual particles do not get bigger. Triple I says the water in the dish evaporates. Explain in terms of the water molecules what is meant by evaporation. And we have only 2 marks, so we are going to write it a little bit shorter. We say that the most energetic molecules at the surface have enough energy to overcome bonds or intermolecular forces and escape. If we had more marks, we can say that they have enough energy to overcome intermolecular forces and increase the spacing between them and the rest of the liquid molecules. Question 5 says a loudspeaker produces a sound wave in air. The distance between the center of a compression and the center of a neighboring rarefaction is 0.10 meters. That's half a wavelength. So calculate the wavelength. It is equal to 0.10 times 2. Since the wavelength is a distance between a compression and the next compression, not the next rarefaction. A rarefaction is in the middle, so that's only half the wavelength. So this gives an answer of 0.20 meters. B says state a typical value for the speed of sound in air. The most common value is 340 meters per second. CI says calculate the frequency of the sound from the loudspeaker. Frequency is equal to speed divided by the wavelength. We divide 340 by 0.20 to get an answer of 1700, and the unit for frequency is hertz. Double I says explain whether the sound from the loudspeaker is audible to a human with normal hearing or not. So 1700 hertz is within the hearing range, so we say yes, because it is between 20 hertz, which is the minimum, and 20 kilohertz, which is the maximum frequency for human hearing. Part D says another loudspeaker produces sound of a wavelength 0.40 meters. Sound from the loudspeaker reaches a sound absorbing surface with a gap of width 0.80 meters. That's double, not too wide for the sound, but still wide enough to decrease diffraction while the sound wave is moving through the gap. Explain whether it is possible to detect sound from the loudspeaker at either point J or at K. So at J, the sound has to spread with a large angle to reach J, but for K, the spreading is with a very small angle, so it can reach K. There is some diffraction going on here, but not as much as to reach point J. So at point J, no sound, since the gap is too wide for that, and at K, there is sound, since it is close to the original path of the wave. So there is a little diffraction going on to reach K, but not enough to reach J. And this is due to the wide gap that the wave has to pass through. Question 6 says a potential divider is made by connecting a light-dependent resistor and a thermistor in series. Figure 6.1 shows the potential divider, a voltmeter, and a direct current power supply connected into a circuit. The voltmeter measures the potential difference across the LDR. Define the potential difference. It is the energy needed to move a unit charge, which is 1 coulomb, between 2 points in a circuit, or between 2 points. Part B says the electromotive force of the supply is E. Describe how the potential difference across the thermistor can be determined using the reading on the voltmeter. So we can say, since everything is in series, that the total EMF of the battery is equal to the potential difference across the thermistor and the potential difference across the LDR, which was in series, which has the voltmeter reading, so plus voltmeter reading. That's like saying in series, the voltage of the supply is divided across the voltages of the components, or divided on the components connected in the circuit. So we have a thermistor and an LDR. We add these voltages to get the voltage of the battery or the EMF of the battery. Part C says the resistance of the LDR decreases and the resistance of the thermistor increases. State what has happened to the light intensity incident on the LDR and the temperature of thermistor. So temperature and light with LDR and thermistor are opposite to what happens to the resistance. So if the resistance of the LDR decreases, that means that the light intensity increased. And if the resistance of the thermistor increases, that means that the temperature decreased. So they are always opposite to resistance. Double I says explain what happens to the reading on the voltmeter now. So we had an LDR connected in series with a thermistor, like this. And we have the resistance here decreasing and the resistance here increasing. And the total voltage of the battery is still the same. So in series, whenever a resistor has a decreasing value, the voltage across it decreases and the voltage across the other components increases. And the voltmeter was connected across the LDR, so the reading on the voltmeter itself decreases. So we say that potential difference decreases since voltage is proportional to or directly proportional to resistance in series or in a series connection, like the potential divider. But we have 3 marks here, so we need to give an extra piece of information. Why is the voltage directly proportional to resistance in this case? Because all components have the same current according to the equation V equals IR. So if I is the same as R increases, V increases. As R decreases, V decreases. Question 7 says a solid bar is inside a copper solenoid. Figure 7.1 shows the copper solenoid is connected in series with a battery and a variable resistor. The device shown in figure 7.1 is an electromagnet. Suggest a suitable material for the bar. That would be iron or soft iron, because it is a soft magnetic material, easily magnetized and easily demagnetized by the current. Part B says the right hand end of the bar is the S pole. Figure 7.2 shows the bar viewed from above. On figure 7.2, draw at least 6 field lines to show the pattern and direction of the magnetic field surrounding the bar. So if this is south side, the other side is the N side, and you can draw oval curves like this, but not touching each other, and the spacing between them keeps increasing. And we draw the mirror image for them on the other side. Nothing is touching each other. And then we draw the direction of the field. The direction of the field is pointing away from the N pole on each line and towards the S pole on the other side. So this is the total shape of the field. Double I says the resistance of the variable resistor increases. Explain what happens to the magnetic field surrounding the bar and state how the pattern of the field lines that represents the field changes. So a resistance in a circuit increases. That means that the current will decrease. So first we say that current decreases. And the current is what magnetizes the iron core. So the field gets weaker since the current is less now. And weaker field is represented by lines that are far apart. So we say, and the lines or the field lines get further apart. Question C says a square coil of many turns is placed close to the bar. Figure 7.3 shows the plane of the square coil parallel to the flat circular surface at the right hand end of the bar. The resistance of the variable resistor is alternately increased and decreased. So the current creating a magnetic field keeps increasing and decreasing, so the magnetic field keeps getting stronger than weaker than stronger than weaker. So there is a changing magnetic field here. Explain what happens in the wires of the square coil which is not connected in this circuit. So a coil or a wire in a magnetic field that is changing gets an induced EMF. So a changing magnetic field induces EMF due to something called the change in flux in the coil or cutting of magnetic field by the coil. First we say as the current changes, it causes a change in flux in the coil and induces an alternating voltage. For example, when the current is increasing, the increase in magnetic flux in the coil creates a positive voltage, and when it decreases, it creates a negative voltage in the coil, or vice versa. Question 8 says the nuclide notation for a radioactive isotope carbon-14 is 14 and 6. Using the symbols shown in figure 8.1, draw a diagram to show the number of electrons, neutrons, and protons in a neutral atom of carbon-14 and how they are arranged. So for the proton number, we have 6 protons, and for a neutral atom, we have 6 electrons. So the total charge is 0. And for the neutrons, we calculate the difference between the nucleon number 14 and the proton number 6. That gives an answer of 8 neutrons. So we draw 8 neutrons and 6 protons in a nucleus. So we have something like this: 1, 2, 3, 4, 5, 6, 7, 8 neutrons, 1, 2, 3, 4, 5, 6 protons, and we randomize the shading. So 1, 2, 3, 4, 5, and 6, and the rest are neutrons. And we have a shell here where electrons orbit. For example, we have 2 electrons in the first shell and another shell. We draw the rest of the electrons, so we have 1, 2, 3, and 4, making a total of 6 electrons. Part B says describe how the composition of a neutral atom of carbon-14 is different from the composition of a neutral atom of nitrogen-14. So carbon-14 was 14 and 6. Nitrogen-14 is 14 and 7. So we have one more proton, but the same number of nucleons means that we have one less neutron. So one more proton and one less neutron in the nucleus. But since we are describing a whole atom, we can say that for a neutral atom, we have one more electron orbiting the nucleus of that. Part C says carbon-14 decays by beta emission. State the name of a particle that is identical to a beta particle. That would be an electron, since a beta particle is a high energy electron emitted from a nucleus. Double I says describe the change that takes place in a carbon-14 as a beta particle is emitted. We say that one neutron changes into a proton and an electron is emitted. Question D says the half-life of carbon-14 is 5,700 years. A very old object is made of wood. It contains 1.2 times 10 to the power of 11 atoms of carbon-14. When it was manufactured, it contained 9.6 times 10 to the power of 11 atoms of carbon-14. So we have the initial number of atoms and the final number of atoms, and there was decay in between. We need to determine the time that has passed since it was manufactured. So since we have the initial and final values, we divide the initial by 2 until we reach the final value. So 9.6 divided by 2, that's 4.8. Divided by 2 again, that's 2.4. Divided by 2 again, that's 1.2. So we have 3 half-lives passing since we had to divide by 2 3 times. That means that 3 half-lives have passed. So we need to get the time for 3 half-lives, and we have the time for 1 half-life, which is 5,700 years. Using cross multiplication or just multiplying 3 times 5,700, we get an answer of 17,100 years. Question 9 says the Milky Way is a galaxy in which the solar system is located. State what is a galaxy. It is a group of hundreds of billions of stars. Some of these have solar systems and some do not. Part B says the Milky Way has a diameter that is approximately equal to 100,000 light years. Determine this distance in kilometers. So we have 100,000 times the distance of a light year, which is the speed of light multiplied by the time, which is 1 year. The speed of light is 3 times 10 to the power of 8 multiplied by time, 365 days times 24 hours times 60 minutes times 60 seconds. But this gives the answer in meters, so we need to divide by 1000 at the end to convert from meter to kilometers. This gives an answer of approximately 9.5 times 10 to the power of 17 kilometers. Part C says astronomers determined the speed and distance from the Earth of a far galaxy that is moving away from Earth. State one observation that allows the speed at which a galaxy is moving away to be determined. That would be the increase in wavelength of light received from the galaxy, or we call that the redshift. Double I says state one different observation that is used to determine the distance to a far galaxy. That would be the brightness of light from a specific object that we know the amount of light that should be emitted from, like a supernova, or just brightness. So we say brightness of a supernova or just brightness. Triple I says state how the speeds of galaxies and their distances from the Earth are related. This is according to the equation V equals H naught D, which is the Hubble equation. And H is a constant, so V and D are directly proportional. And the graph between V and D is a straight line through the origin. IV says the best estimate of the Hubble constant is 2.2 times 10 to the power of negative 18 per second. Use this value to calculate an estimate for the age of the universe. We calculate the age of the universe as 1 over the Hubble constant. So we divide 1 by 2.2 times 10 to the power of negative 18. That gives an answer of approximately 4.5 times 10 to the power of 17 in seconds. If it was required in years, we divide that by 365, 24, and 60, and 60. So this was the end of the exam. I hope you enjoyed this video and found it useful. Keep practicing, and I will see you in another video.